All right, we're going to start by the problem-solving process by looking over last night's homework problem. A bus moving at 26 meters per second slows at a rate of 3.5 meters per second each second. Find when and where the bus stops. So in this picture, I just drew a bus. All right, yes, that square with two kind of wheels is a bus. To the right is positive, to the left is negative, and I defined an origin. All right, so we've been able to sketch this situation. We chose a coordinate system. We indicated the origin and the direction, the positive direction and the negative direction. Now we have to sketch this with relevant information. Looking at the relevant information in this problem, we find initially that the bus has initial velocity of 26 meters per second. Okay, I apologize for the handwriting on this. This is my first time through, so it might be a little iffy. All right. And they're asking when and where the bus stops. So we're looking sometime later where the bus is going to eventually end the problem. We're just going to mark this the final position, which we don't know. And then the bus stops. This implies that the velocity of the bus has gone to 0. So my final velocity, I'm going to write as 0 meters per second. Okay. We are also given the rate at which the bus slows. And according to this, it's 3.5 meters per second per second. So that would be the acceleration, and I'm going to label that in between because that's what occurs in between the start and the finish of the problem. It changes its velocity. So we have meters per second, and the time also occurs in between, and we don't know that, so that's going to be left as a question mark. Now we can follow this logically in order from the initial, what happens in between, to the end of the problem. So the next part is construct a physical representation, which means motion diagrams and position versus time and velocity versus time graphs. So we're going to begin by drawing a motion diagram. Since the bus is moving at 26 meters per second and slows at a rate of 3.5 meters per second each second, we're going to draw a motion diagram that shows the bus slowing down. So on here, I have V1, and my V arrow should be getting smaller. V2, again, I apologize for the terrible handwriting here. I'm still getting used to this. Alright, so we have our V arrows getting smaller, and if they're getting small, that means our change in velocity arrow is going to be pointed in the opposite direction. So our change in velocity arrow is going to be pointed to the left. I'm going to label this delta V. Now we can also draw a velocity versus time graph. Alright, the velocity versus time graph, like I said, come over here. Alright, so apparently I can draw some straight lines on this. T here, velocity here, we know it's going to be in meters per second. Starts at 26, and as time goes on, we'll go back down to 0. So that's my velocity versus time graph. We'll get to position versus time, but we'll leave it out for this case. Alright, so now I have a bunch of representations, and I need to check for consistency. So looking at this, my V arrows are pointing in the positive direction, which means I should have a positive, initially, 26 meters per second on my velocity. So when 26 is positive, that's good to go. We look at this here, the 26 is also positive, the arrow is pointing to the right in the positive direction, so again, the velocity arrow is good to go. Now the acceleration direction, if I look at my delta V arrow, it's pointing to the left. If I also look at the slope of my velocity versus time graph, it is a negative slope. So by leaving this here as a positive 3.5 meters per second, this is not consistent with the other two. So what I want to do is I want to add, a negative sign. That's the worst negative sign I've ever seen. Undo. Let's try this one more time. Negative sign. Alright, it'll have to do for now. Alright, now we can start to address the question. When the question asks when and where the bus stops, it means it's looking for the time frame and the location where the bus stops. So we're going to handle the time frame first. If I look at my givens, I'm giving the initial velocity, the final velocity, and the acceleration, which means I can use one of our kinematic equations to solve for the change in time. So I'm going to first write that equation in variable form. okay? VF is equal to VI plus A delta T. All right, I want to solve for delta T, so I'm going to show the manipulations without plugging anything in. So I have VF minus VI divided by A is equal to delta T. And then I can substitute in the numbers. So I'm going to have my final velocity, which is 0 meters per second, minus 26 meters per second, divided by the negative 3.5 meters per second is going to equal, and then I can solve for this, and it's going to be 7.4 seconds. Now, you will notice that if you didn't put the negative sign into the 3.5 meters per second, that value would be a negative time. Negative time doesn't exist, so your answer wouldn't make any sense. So you can use the signs to check kind of your work. Once I have my answer, I will box it, okay, and we'll move on to when and where. All right, so now we're going to look for where the object is after that period of time. All right, looking for that, we can use the kinematics expression we derived yesterday. Delta x is equal to the initial velocity times delta t plus 1/2 a delta t squared. Okay, we know our initial position is 0, so our change in position is going to be our final position minus 0, which will also end up being our final position. All right, if we substitute the numbers in and include the signs for the initial velocity times the time, we should get 192.9. That's a terrible 9. Let's see if I can redo this quickly. We should get 192.9 meters minus 96.3 meters. If you subtract the 2, this is going to be 96.3 meters. And then, since our initial position is 0, we know our final position is 96.3 meters. Okay, this is how you go about this, solving pretty much all motion problems. Okay, you follow this process. Sketch and translate. Draw your representations, your motion diagram, your velocity versus time and position versus time graph. Represent it mathematically, solve and evaluate. See if this makes sense. Well, if we started at 0 and moved in the positive direction, our final position is positive. Our time is a positive time. We used our other representations to check for the consistency of the acceleration. That's going to be key. All right, in the finding the final position, if you had your acceleration as positive, you would have gotten somewhere just shy of 300. All right, so you really have to pay attention to the signs. The signs are extremely important, and that's why we spent a lot of time today on motion diagrams and the signs of everything. So please, when you go through the other two scenarios, scenario number 2 and 4, follow this process. This process is pretty much the way you're going to solve all problems, and I expect you to understand this process. You can then apply it to anything. All right. So make sure you go to our Encore site, download the problem-solving strategy, and try scenario number 2 and number 4. That will be your homework this evening. Have a good night. If you have any questions, please shoot me an email.